Hi there, my name is Esme and I'm a member of FRC Team Through and 2-8, the Aluminum Narwhals. We're Canyon Crest Academy's first robotics competition team, and over the next few weeks, we're super excited to introduce you to some concepts in science and engineering that we think are really cool. This week, my teammates and I are going to be introducing the basics of simple machines and how they apply in everyday life. At the end of this lesson, you'll even get to build your own out of things that you have around your house. Have fun! Essentially, simple machines are tools that help us move things. But to understand what they really are and why they're so helpful, we need to understand a few core concepts in physics. The first is the conservation of energy. This is the idea that energy cannot be created or destroyed within a system. So think about if I have this box here and I want to lift it up in the air. The box is going to gain energy by being higher in the air, but when I lift the box, I'm going to feel tired because I'm losing energy. That's the idea that we can't create more energy. I'm going to lose energy, but the box is going to gain energy. That's conserving the total amount of energy in the system. Now, the interesting thing is when I'm lifting the box, I'm doing what scientists call work. Work is a measure of energy transfer as an object is moved by a force. So when I lift the box up in the air, I'm moving it a certain distance by applying a force upwards. I'm either pulling or pushing the box up to get it into that place. So when we do work, we have a way of quantifying how much work we've done. Work is equal to the amount of force that you apply, so the amount of push or pull that you do, times the distance that you apply this force over. So in this case, I would multiply the amount of force that I apply to lift that box up in the air times the distance that I move that box. That's what we call the work that I've done to the box. Now, work is really interesting because it's essentially a measure of energy transfer. So work and energy are both measured in a unit called joules. The interesting thing about work is because you're multiplying two things, multiplying force and distance, you have many different ways of transferring the same amount of energy. So to lift this box up in the air, I could either lift it straight up by a set amount of distance, or I could find a way to apply less force over a longer distance. And that will still be the same amount of work, which is something really interesting and a principle that simple machines take advantage of, as you'll learn later on. Let's think about what that equation means in terms of an example. If I were trying to lift up a box that weighed 10 newtons, newtons are a measure of force or weight like pounds are. If I was trying to lift that up 2 meters, how much work would I need to do? Well, if the force is all going in the same direction that the distance is moving, so if I'm always pushing straight up, then that force is equal to 10 newtons, and we're moving it 2 meters. So the amount of work that I have to do is equal to 10 newtons times 2 meters. We can also call that 20, which you might recognize as a unit of energy. So now we know a really important detail. If you're trying to lift up a box so that it gets 2 meters off the ground, it's always going to take 20 joules of energy. But what about if we don't want to lift it straight up? Because sometimes lifting something really heavy straight up in the air can be hard. What about if we use a ramp? Well, in this case, the box is still going 2 meters up in the air, as you can see, but instead of lifting it up 2 meters, we're pushing it 5 meters up this ramp. So in this case, the work is 20 joules, since the box is getting to the same place, and that is equal to the 5 meters that we push it, times the force in this direction that we're applying to the box. So take a minute now to think about what value for that force, when you multiply it by 5 meters, will get you to the 20 joules of energy that you need to push the box all the way up that ramp. That value should be 4 newtons, since 4 newtons times 5 meters equals So this is a really important concept that simple machines take advantage of. If you apply less force over a longer distance, you can do the same amount of work to accomplish a task. Try and think about some things that you do around the house every day. Whether it's chores or reading a book or doing some homework, are you doing work in a physics sense? Are you applying a force or a push or a pull over a set distance?
Hi, my name is Shannon and I'll be showing you guys how pulleys can help us carry or move heavy loads. First off, what's the heaviest thing you've ever tried to lift? Maybe a table? Maybe a really heavy box? Maybe even a car? But I doubt any of us could lift a car by ourselves. That's why we have simple machines, such as pulleys, to help. A pulley is a collection of one or more wheels in which you loop a rope into to make it easier to lift things. Let's say we need to lift a piano up to the 3rd floor of an apartment. We wouldn't want to carry it all the way up, right? That would be extremely difficult. So we can use a pulley. If you look at this picture, when the man pulls down on the rope, the piano moves upwards. The force that the man puts on the rope is called effort. The weight of the piano is called the load. With this example, the effort is equal to the load. So, if the piano weighs 1,000 newtons, which is a little over 200 pounds, the man has to pull down with the force of 1,000 newtons. This is because we only have one pulley. In this case, the fixed pulley just redirects the force. So, instead of pulling upwards without a pulley, the man just pulls downwards with the pulley. If we increase the number of pulleys, it becomes much easier to lift an object. With this, we have 2 pulleys. The amount of effort you need to exert on the rope can be calculated by the weight of the load, which is 1,000 newtons, divided by the number of ropes, not counting the one that you're holding. So, in this case, we would have 2 ropes. The effort would be equal to the weight of the piano, which is 1,000 newtons, divided by the 2 ropes that we had counted. The effort is equal to 500 newtons. As you add more pulleys, you increase the mechanical advantage, and it becomes easier to lift a load. The only trade-off is that there is more rope to pull in order to lift the same load. In this case, more rope equals less effort. Using the equation from before, can you calculate the effort needed to lift the 100 Newton load for each of these pulley systems? Pause the video and try it out. Remember, the effort is equal to the weight of the load divided by the number of ropes. For each of these, I calculated the effort using the weight of the box, which is 100 newtons, divided by the number of ropes. Pulleys can be found in all sorts of things in your everyday lives, such as gym equipment, elevators, flagpoles, garage doors, and much more. Can you think of any other places pulleys are used?
The next simple machine we're going to be talking about are wedges. Wedges have triangular cross sections, meaning they start out wide at the top and then narrow down to a point. What's really cool is that wedges have a bunch of different applications. First, they can be used to cut or split. So when you're cutting up food with a knife, that knife is a wedge. Or if a lumberjack is trying to chop a log in half, they're using a wedge to split that log. They can also be used to hold things in place, so that's something like a doorstop being used to stop a door from closing. And lastly, they can be used to scrape up something. So I know we don't get snow in Southern California, but if you were to use a snow plow to try and lift the snow off of the ground, that snow plow has wedges in it that's doing that scraping. Now let's talk about how wedges work as a simple machine. As we said earlier, simple machines work by changing either the direction or the magnitude of a force or both. When you use an axe as a wedge, like in this picture that we have on the left, you apply a force to the top, the wide part of the wedge. And then this force changes its direction and its magnitude. So those 2 orange arrows are the output forces that help cut the log in half, because you can see both of them are pushing away from each other, so the two sides of the logs get pushed away from each other and it separates. And think about that process of hitting down the wedge and the wedge doing the separating is a lot easier than if you were going to try to rip open the log with your bare hands. Like we said earlier, simple machines utilize the principle of mechanical advantage to make work easier. In the case of a wedge, the mechanical advantage is the length divided by the width. So if we think about a wedge that is 2 times longer than it is wide, that has an ideal mechanical advantage of 2. That means if you put in 1 newton of force, it's going to output 2 newtons of force. But remember that the energy that's used to split this has to be constant. So the output force is going to be applied over a shorter distance than the input force. That means that the work is held the same, and we're conserving energy as we have to. So now take a moment to think about which one of these wedges has a larger mechanical advantage based off of that ratio that we just talked about. The one on the right is the one with the larger mechanical advantage, because it's a long, thin wedge, as opposed to the one on the left, which is wider and shorter. That means that the one on the right is going to output more force for the amount of force that you put in initially than the one on the left. Now take a moment to think about all of the different wedges that you see in everyday life. Because they have so many applications, they turn up a lot, so try and list as many as you can.
See, wheels are everywhere, and they make our lives a lot easier. Can you think of some examples in your life where you use wheels? Great! I thought of things like cars, bikes, and wagons, but there are all sorts of ways in which we use wheels and axles in our lives. Today, I'll be explaining how wheels and axles work and the ways in which we use them. First, let's look at a wheel and axle system. Here, we have an axle and a wheel. The two are connected, so if I move the axle and rotate it around, the wheel will move as well. We can use this in several interesting ways. For example, let's look at a bike and Ferris wheel. Here's a bike and Ferris wheel. In a Ferris wheel, we don't just physically push this whole giant wheel. That'd be a lot of distance. Instead, we have a motor pushing the smaller axle here, which makes the huge distance of pushing this giant wheel around. Like, let's look at our wheel and axle model. Here, if we turn the axle, we're actually moving the axle a very small distance around, but the wheel moves a lot larger distance around. Same way in this Ferris wheel, we push the axle smaller distance, but the whole wheel moves this much larger distance. However, this does mean we have to put a lot of power when pushing this axle. The same way works in a bicycle you might ride. When you pedal the bicycle here, it pushes the small axle around and around, which in turn pushes this giant wheel. It does take more power, but you are getting more distance by pushing this much bigger wheel. Now, let's look at another way that we use wheels and axles. Let's imagine that I have to pull this bucket up from like a well, and it's full of water and very heavy. Now, if I were to pull along this axle and turn the axle to wind up the bucket, it would take a lot of force. So instead, we can turn this much larger wheel around. When we turn this wheel, we will be moving the wheel a larger distance, but it'll actually take less force on our part, less effort. So it'll be a lot easier for me to push this wheel around than push this smaller axle around. Although I will be moving a larger distance, it'll take less effort and still move this axle around. The axle will be moving a smaller distance around, but it'll take less effort. We can describe the two kinds of wheels and axles with two different models. In the first example, with the bike and Ferris wheel, we moved an axle a smaller distance but with a larger effort in order to get the wheel to move a larger distance, carry a smaller load. In the other example, with the bucket and the well, we move the wheel a large difference but with a smaller effort, to get the axle to move a small distance but be able to carry a very large load. Here are some other examples of wheels and axles that we see in our lives. Some other examples of wheels and axles are things like gears, capstans, and these belt drives, which you see in engines. Now that we've described some examples of wheels and axles and the two ways in which wheels and axles work, can you think of 2 examples of how wheels and axles work in your lives? Thank you for watching. Have a great day. Bye!